people not here today. So, Mrs. Bad Crumble made you draw factor trees, and you drew them. And Mrs. Bad Crumble, when you drew them correctly, Mrs. Bad Crumble gave you a star, and you were like, yeah! And then it was over, right? You got your star, and then since that first day you drew your factor trees, you've never drawn them again, right? Sometime around grade 5 or 6. This isn't complicated, Gideon. Just sit in a desk. You got here late, just sit down. So, the thing that I don't like about math, the way we teach it in Canada, is we'll teach you something, and then we won't talk about it for 5 years. And then we'll expect you to remember it and be able to do it, right? In other countries, they don't do that. They teach you a concept, and then they follow that concept through for quite a while. So a kid in grade 3 who's just learned to add fractions may very well learn how to deal with rational expressions, which we don't do again until grade 11. Everybody understand? So we're going to bring back one of the oldies, an oldie but a goodie from math back in the day, factor trees. But before, of course, we draw a factor tree, we have to explain a couple of things, the terms. For one, we have to know what a factor is. What is a factor in English? Not math class. What is a factor? Roman.
Like something that can change a situation.
Yeah, absolutely. Good. That's a good analogy. There's a factor in my mood in the class, yes? If all of you did all of your homework, and I walk around and do a check, and everybody's got a check plus, I'm happier. Your behavior is a factor in my mood, yes? Just the other way around, too. If I spend the whole class yelling at you and telling you guys are dumb, which I would never do because you're not, but if you had a teacher that did that, you would not like that teacher. Right? Okay.
And another one be like something that kind of leads to...
Yes. Yes. So now that we all know what factor means in English, we apply it to math. It applies to a specific operation, math, which is multiplication. And the factors are what makes what? The product. Right. How many factors can you have of something? As many as there are, right? Sometimes there's only 2 factors. If there is a number with only 2 factors, what kind of number is that? A prime number. They are the most powerful numbers and, quite frankly, the most amazing numbers because there are prime numbers up in the billions, which is insane to me that a number that big can have no other factors. But it is true. Number theory is neat. So, we know what a prime number is. Other than that, there are a few ways to do factors. Ethan.
Sorry, I thought we were still talking about prime numbers.
We are.
Oh. Can I explain what one was? But you kind of just didn't know.
You done?
Yeah.
Okay.
Going to explain.
I don't want to quash your creativity.
No, that's okay.
But if you wish to, you can.
It's a number that can only be divisible by itself and 1, and it has to result in, and its division has to result in a whole number.
Yes. All right. So is 1 a prime number?
Yes.
No. 1 has how many factors? 1. No. It has 1 factor. 1. Is 0 a prime number? No. Is 2 a prime number?
Yes.
Why is 2 the most powerful prime number? Ethan. Yeah, it's the only even prime number. So it's extraordinarily powerful. I would argue it is the most powerful number in our number system. Now, I just read a book recently that prime numbers were quite prominent in, and the author of that book feels 97 is the best prime number. I don't know why. He just kind of threw that in the middle of the paragraph, that 97 is the best prime number. And since I read the book, I've been thinking about what makes 97 great, and I can think of nothing except that it was, I think it's Connor McDavid's number, isn't it? But I don't know.
Maybe he's trying to compensate to make his age seem cool.
I don't know. It was a really good book. I thoroughly enjoyed it, but that's another story for another day. So we know what a prime number is. Excellent. We know something about factors. When we use factors, we use that word all the time in math. We talk about factoring things all the time. It means a lot of different things. For example, if I say factor 12, what would you do? Gideon first, then Ethan.
List all the whole numbers that multiply into 12.
All the whole numbers that multiply into 12. So you would write 1, 2, 3, 4, 6, and 12.
Yeah.
Okay, is that what you were going to say, Ethan? Excellent. Okay. Now, when I say factor 12, and you say, there's all the factors of 12. Does that mean that I could choose any two of them and make 12? No, what does it mean?
You would have to pair certain ones.
I got to have specific pairs, right? 12, 1, 2, 6, or 3, 4. Yeah? Hey. Right? Everybody understands that? Yeah. Okay. So when we say factor, we could mean list them all. We could mean give a pair. Could we do this? Are these factors of 12? Why? Look. Right. So that's another way to factor. Everybody understand? It means a lot of stuff. Okay? All right. So for our purposes, we are going to be using factor trees, and we are going to be finding prime factors. So a prime number, we've already said, Ethan has told us, it's any number with only two factors, 1 and itself. Right? We already know what that is. So if we're going to do factor trees for our purposes and what we are going to grow this into, we need to do prime factor trees, which means if we are going to keep with that analogy of calling this a factor tree, each branch must end in a prime number. If it doesn't end with a prime number, we must continue to grow the branches. Everybody cool? Now, many people, many teachers draw their factor trees in many different ways. I do not care how you do what I am about to do. All right? I am going to go with the method or the representation that I think you are most familiar with, the way most of your Mrs. Bad Crumbles would have drawn a factor tree, and that is going downwards with diagonal branches. Is that how most of you have seen this? All right, so let us carry on then. I would like you to do factors, prime factors of these two numbers, which means we have to split this first one. Now, everybody write two factors of 54 here. There are options. It does not matter what you write there as long as it is a pair of numbers that multiply to 54. You all have 3 seconds. Go. You've already done it. I see that. All right. How many people chose the obvious answer of 18 times 3? What?
27 times 2.
You goofs. Most of you probably did 6 and 9, right? Some of you might have done 27 and 2 because 2 is a prime number, right? But I bet nobody did 18 and 3. Anybody? Yeah. All right. So, anyways, I am going to go 18 and 3. Can either one of my branches stop now? Which one? The 3 can stop, so I'm going to circle it. 18 can't stop. Now, you take your 9s and 6 or your 27s and 2s and continue to break them down. And 6, 3, and 2. And you can quite plainly see that I have 54 equals 2 times 3 times 3 times 3. Now, would any math person ever write it that way? Of course not. How would they write it? 2 times 3 cubed, yeah? Yeah. Now, let us do the same thing with 162, please, cabbages. Go. I am betting that you chose the obvious first two factors of 9 and 18. Of course, right? No? Oh, I bet you took the easy way out and did 2 and 81. Losers. Okay, why am I making this joke? Because does it matter? What if you follow all the branches down, we get the same answer, don't we? There is no right first two factors to use, as long as they are factors of the number you are factoring, okay? So, I went with 9 and 18 just to be a dink. You all went with 2 and 81. Keep breaking it down. 3, 3, there's my 2 primes. 3, there's another prime. 6, that's not prime. 3, 2, and we get 162 equals 2 times 3 times 3 times 3 times 3, which, of course, is 2 times 3 to the 4th. Yeah? Yeah. Now that we have done that factoring, there are two things that you can do with it. One of them is for finding the greatest common factor. Now, what we are doing today, greatest common factor and lowest common multiple, are very important in data. And that, ladies and gentlemen, is the wave of the future. That is the industries where we need to be able to function, right? Building stuff is disappearing. Data is where it is at. And this type of calculation comes into play with data. So a greatest common factor. First of all, they are called GCF. We will use that term all the time. Now, factors. Are factors whole things, or are they parts of other things? Parts of other things. Factors can never exceed the number with which you are working, right? I can never have a factor of 54 that is bigger than 54. Everybody cool? So factors are always smaller than the numbers you are working with, which is weird because it's called greatest common factor, but the answer is going to be smaller than the numbers you are working with. Everybody can wrap their minds around that, yes? All right. Now, greatest common factor is the factor with the largest value shared by a group of products. Okay? Pretty easy. 54 and 162 are obviously numbers that are products of other numbers. They have factors. Whatever factor is shared by them, that is the largest, is their greatest common factor. Okay? The smallest it can be is 1. What's the biggest it could be? No. Right. So 54 or 162, which could it be? A GCF of 54 and 162. What's the biggest number it could be? 54. Because the biggest factor of 54 is 54. It couldn't possibly be bigger than that. Everybody cool? All right. We find the prime factorization. This is weird, so pay attention. Once we have the prime factorization, we can find the GCF by, collecting all the common factors, grouping by lowest exponent. Now that seems weird, right? Because we want the greatest common factor, but we're going to use the lowest exponent. Please highlight common. Put a Mrs. Bad Crumble cloud around common. Put some stars by it. Underline it. I don't care. That word is utterly important to this definition. We're not going to do that yet because we're going to... actually, we are going to do that. So let's find, using my black ink, the GCF of 54 and 162. So the first thing I do is I list them. I know the screen just went blue. You can list them. 54 is 2 times 3 cubed, right? So you're going to write 54, 2 times 3 cubed. Then you're going to write 162, and that is 2 times 3 to the 4th. And then you're going to have two little lists, one on top of each other when the screen comes back on, and then we're going to talk about it. Although you probably already know what is happening here. What is common to both of them? 2. What is the lowest exponent of 2 that is common to both of them? 1. Okay. Is 3 common to both of them? What is the lowest exponent of 3 that is common to both of them? 3 to the 3rd. So that means the GCF of 54 and 162 is 2 times 3 to the 3rd, which is 54. And that makes sense because 1 times 54 is 54. So 54 is a factor of 54. And 54 times 3 is 162. So 54 is also a factor of 162. Everybody cool? All right. The next line says lowest common multiple. And it is nicknamed, obviously, LCM. Now, you already know how to do lowest common multiple. You've been doing it forever, except you call it lowest common denominator. Right? Because how do I add 1/2 and 1/3? Right, and you get 1/6. Right? Now that's the shortcut that you're always taught when you're first doing adding fractions. Just multiply them by each other. That will get you a common denominator. Often it's the lowest common denominator, but not always. So a lowest common multiple, I'm going to change to red ink so it's less confusing. A lowest common multiple is the smallest number which shares a group of numbers as factors. So, a multiple is getting bigger from where we started, right? Because factors are the parts that make up multiples. So if the biggest factor you can have is the smaller number in your group, what is the smallest multiple you can have? Here's our group. Oops, that should have been highlighting. Here's our group. We know that that is the biggest factor we could share, right? So what is the smallest multiple we could share?
Wait, no.
Multiples are bigger. This is the biggest factor we could share because 54's biggest factor is 54. Multiples are bigger. Factors are parts of these. Multiples have these as factors. They are going up from there. So what is the smallest multiple we could have? Hatisha, is your hand up or are you just... Okay, Gideon? 162. Because 162 times 1 is the first multiple of 162. Everybody cool? All right. So we find it in a similar method, but slightly different. Because we are building upwards, we have to count everything, but just once. So here we find, I got to get my red ink. The LCM can be found using prime factorization by, not G, counting all, not just common. Counting all with our Mrs. Bad Crumble Cloud. All the factors, but by greatest exponent. So, we'll list them again. We know it's 2 times 3 cubed and 2 times 3 to the 4th. We have to count them all, but only by greatest exponent. Is 2 one of the factors? What's the greatest exponent of 2? The greatest exponent of 2 visible there is 1, right? So it's 2. Is 3 in both of them?
Yes.
What's the greatest exponent of 3? 3 to the 4th. So that is 162. And we already know that's going to be the right answer because of what I said just earlier, right? 162 times 1 is 162. 54 times 3 is 162. Is everybody cool? Now, where kids mess up is they have no problem seeing these two because all the numbers are the same, right? We can easily understand why it's the smallest number here, right? Because we're factors, we're going smaller, yes? And we can see why it's the biggest exponent here, because it's multiples, we're going up, right? When kids have issues is when there's another number here. For example, if we weren't doing 54 and 162, we were doing 162 and 270, then this 54 would also have a 5, right? And this would also have a 5, right? I've changed colors to blue because now we're going to do 162 and 270, right? So now, what's our biggest common factor now? It's still 54 because the 5 is not part of the 162. Does everybody understand? And over here, we have to bring this 5 to the party now because 5 is a part of 270. So we have to multiply that by 5 to get 810. Everybody cool? In GCF, because we're only counting parts, we can only count the common things. But in multiples, because we're going upwards, if I don't bring this 5 to the party, right, then 162 becomes my lowest common multiple. But 270 was the number I was working with, right? So I have to keep that 5 to cover the 270. Okay? That's why we made such a big deal out of common and such a big deal out of all. Everybody good? Okay, we're going to practice this 4 times on the next page, and then you're going to practice it a bunch more. So, first step is always what? Start your factor tree. Now, if you do your factor trees differently, by all means, do them differently. I don't care. Obviously, you're going to start 36 with Why wouldn't you do 18 and 2?
19 and 4, or 9 and 4.
Why wouldn't you do 9 and 4? Why wouldn't you do 3 and 12? Why, Mackenzie? Because it doesn't matter. Whatever I write here, even though I'm making a big deal out of this, if I write 9 and 4 here, I will see some of you do this. Erase? Oh God, it's supposed to be 9 and 4. Even if you wrote 3 and 12, which is perfectly acceptable, some of you would erase it still. Don't. Carry on. 3, 3, 2, 2. All those are prime. So 36 is 2 squared times 3 squared. Yeah? What's 120? Obviously, you're going to go... No, you're not supposed to say anything here because everybody's going to do something different. Obviously, you're going... There is no obvious right answer, right? Obviously, it's 10 and 12. Because 10 times 12 is 120. It ends in 0. Why wouldn't you use a 10? A dir. Does it matter? No. Carry on. 2 and 5. 2 and 6. Prime. 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 2 and 3. Prime. Prime. 120 is 2 cubed times 3 times 5. Right? Yeah? Okay. So what is our GCF? GCF is the parts, right? So we remember the biggest number it can possibly be is 36, yes? So since 36 is the biggest number it could possibly be, do we care about this 5? No, because 5 isn't part of 36. So when we're doing GCF, we don't care about anything that isn't common. Right? So these are common, yes? Which one do I need in GCF? Which shows me the biggest part? Is it 2 squared or 2 cubed? 2 squared, because we are looking for parts. We are shrinking down. 2 squared. What about 3's? They're both there. Which one do we need?
3.
Just the 3. 2 squared is what? 4 times 3 is? So 12 is our GCF. Everybody cool? Our LCM. Change color. I'm feeling green today. I'm feeling like Kermit. It's not easy being green. Anyone? Kermit? Kermit D. Frog here.
What's a Kermit?
My dog's middle name is Declan, so he can be Cooper D. Dog. Because that's why Kermit's middle initial is D, because he's Kermit the Frog, Kermit D. Frog, Cooper D. Dog. Anyways. LCMs, now we're going upwards, yes? So go. 360. Why? Because we need the upper ones now. So we need 2 cubed times 3 what? Squared. And why do we need the 5 now? Because we're going up. So 5 is part of 120. 120 is the smallest number it could be. So we have to continue. We have to use that 5. And as Locke says, 2 cubed is 8. 3 squared is 9. 8 times 9 is 72. 72 times 5 is 360. Yeah? Yeah. Go. 18 and 24. Hit me. Don't really hit me. It will end badly for both of us. I'll get fired and you'll be crying. I'm just kidding. Locke.
For LCM, can't you just find the first number that both of them are multiples of?
Yes, of course.
So I don't
No, you don't have to do this, but when we get more and more numbers and bigger numbers, you will find this to be very helpful, right? What Locke is saying is, couldn't you just have gone 36 times 1? Well, you wouldn't even have to do 1. You would start at 4, right? Because 36 times 4 is 144. So it's not that. 36 times 5 is 180. Well, 120 doesn't go into 180, right? So you keep going. Then you get up to 36 times 10, 360. 120 times 3, 360. That's what it is. Easy when the numbers are close or small. Or that they work so well together. Like 12 is a multiple of 36, right? When you see numbers, it's easy. So 18 and 24, obviously, what are we starting with? I didn't get any of you. Nice. 2 and 9, 3 and 3. 2 times 3 squared. 24. 2 and 12. 2 and 6. 2 and 3. 2 cubed times 3. GCF is what?
6.
Right, because it's 2 times 3, which is 6. LCM? 2 cubed times 3 squared, which is 72. And again, you could do this just by counting. 24 times 2 is 48, times 3 is 72. 18 times 4 is 72, obviously 72, right? But if we were doing this with a group of 5 numbers, it's easier to do this. Everybody good? All right. You do letter C all by yourself. When you get to D, I'm going to mess with your heads a little, and I'm going to add uh, 91. No, too easy. I'm going to add 112. That's the stuff. So for D, you're going to have to do this 3 times. Without yelling it out, pull on your right ear if you feel you have the right answers to C. Pull on your right ear if you feel you have the right answers to C. I like how some people went with the cross pull. They reached over with their left hand. If you were in a gunfight, would you put your guns like an old Western guy backwards so you could cross draw? It's badass, I know. That's the way I do it too. I would totally go cross draw. Roy? 112. All right, what is the LCM for C? Lockhart? 225. What is the GCF for C? Abby? 15. Absolutely correct, Abby. And bonus points for not being all like certain other people I could mention. All right, start working on D. this time, pat your tummy when you think you have the right answer. Don't look around, just pat your own tummy. It's nobody else's business. Pat your what? Tongue. Ooh, gross. Tummy. Who has an answer for me? What is it? Oh, wait, sorry. What's the GCF?
I think it's 7.
It is absolutely 7.
But I didn't do it properly. I just knew it was 7 because it's obvious. I don't know how to do it that way. Yeah.
I'll show you.
Yeah.
What's the LCM is big, isn't it?
Yeah.
What is it? Roy?
1,680.
1,680. Well done. Now, Locke is saying, and brave of him to say he's not sure how to find the GCF. Here it is. There's my lists, yes? Right? I can only count stuff that's a part of all of them because it is greatest common factor, greatest common part, right? So 2 is not in all of them, is it? So 2 can't be part of the GCF. 3 is not in all of them. So 3 can't be part of the GCF because 3 doesn't work with 35 or 112. 5 only works with 35, so it can't be 5. It had to be 7. Everybody understand? Now, what if this was 70? Now what would I have right here?
3 would be.
I would have 2 times 5 times 7, wouldn't I? To get 70, 2 times 5 is 10, 10 times 7 is 70. And now is 2 common to everything? So the GCF would then have a 2 added to it, and it would become 14. Is everybody cool? You good now? I heard one person say, what?
Where did you get 70 from?
I just changed it to 70. I said if it was 70, what would the black line become? When it was 35, it was 5 times 7. So now I'm asking you, what would happen if I made it 70? It would be 2 times 5 times 7, wouldn't it? And that would make 2 a part of all 3 of them. So the 2 would have to become a part of the GCF. So my GCF would now be 14.
Yes, okay. But what about 35? How would you know?
35 isn't there anymore, Gideon. That's what I said. What would happen if it was 70 instead of 35?
Okay.
So 35's gone. Forget about it.
How do we do it if it was?
If 35 and 70 were there,
No.
we did it when it was 35. That's what the 7 is. That's what 7 was. That's when it's 35. I don't even know what you're asking. I want to answer your question, but you're not, I don't get it. What?
And it's because the lowest exponent in both sides would be 1 because it's a singular 7, making it 7, right?
Yes.
Okay.
Because it's got to be the parts,
Yeah.
right? If I counted all 3 of those 7s, 7 times 7 times 7 is bigger than 35. It can't be, right? Everybody good?
Can you repeat the greatest common factor why it's 7? Because I was trying to figure this out.
Okay. There's our list, right?
Yes.
We need the biggest part of all 3 numbers, yes?
Yes.
Okay. Is 2 a part of all 3 numbers?
No.
No. So 2 can't be part of the greatest common factor because it isn't a part of 35. Is 3 a part of all 3 numbers? So 3 can't be a common factor. Is 5?
No.
So 5 can't be a common factor. Is 7? Yes. So the GCF has to be 7. Why is it only a singular 7? Because there is only one 7 that is a part of all 3 of them. Now, what I did to change this was I took out the 35 and I said now it is 70, 84, and 112. So this 5 times 7 now has a 2. So now there's a 2 in all 3 of them, but only one singular 2. And there's a 7 in all 3 of them. So if this was 70, our GCF would be 14, because it would be 2 times 7. Okay? What if I made it 115? This would now be a 3. Now what is my GCF? Still 7. Why? There's no 3 here. What if I made this 336? What would be there? A 3, because 112 times 3 is 336. Now what would my GCF be? 3 and 7, which would be, Roy? 21. Does everybody get it? Okay. Your job is to do page 32, but only the left-hand side of the page. Now, listen to me. If you know how to do the prime factors of 600, is there any different skill in doing the factors of 6,125? No. So do you need to do all 6 of them? No. Who decides on your level of competence? You do. If you are the type of person that needs 6 practice questions to be comfortable, do all 6. If you are the type of person, like most kids, I can do one of them. I can obviously do them all. I will make immense amount of fun of you when later in the year you say, I need some help with number 5. And I show you number 5. And then I walk away. And then 2 seconds later, I need some help with number 6. And it's the exact same question. Do you understand? Practice as much as you need to. Same thing for 9. Same thing for 11. 13 and 22 are word problems. You have to think about it. Your only option is GCF or LCM, yes? So you just have to decide which is the logical one to apply to those 2 word problems. Remember, GCF is looking at the parts of a group, and multiples are looking at what a group can grow into. Okay? I know the screen just died, but fortunately it is not important for right now. Go.